There is a moon in our solar system that should not exist the way it does, not in the sense that it breaks physics or defies explanation, but in the deeper, quieter sense that everything about it points towards something impossible. It is too smooth, it is too young. It moves in a way that generates heat it has no right to generate, and buried beneath a shell of ancient ice, completely sealed from the universe above, there is an ocean larger than every body of liquid water on Earth combined. That ocean has been sitting in the dark for billions of years. No sunlight has ever touched it. No atmosphere breathes above it. And yet the conditions for life are not merely present on this world. They are stacked, one on top of another, in a way that makes scientists use words like inevitable and compelling rather than possible and speculative. The moon is Europa, one of the 4 large moons orbiting Jupiter discovered by Galileo in 1610. From a distance, it looks almost peaceful. A pale white sphere crossed by long brownish-red streaks, like a cracked porcelain ball someone dropped and tried to glue back together. It is slightly smaller than our own moon, about 3,100 kilometers across. Nothing about it from afar screams urgency. But then you start looking at the surface more carefully and the strangeness begins to accumulate. The thing that bothers planetary scientists most about Europa is not what is there. It is what is missing. When an asteroid or comet smashes into a solid body in the solar system, it leaves a crater. Simple as that. The solar system is old, and old worlds are cratered worlds. Our moon is covered in them. Mars is covered in them. Mercury is practically made of them. Even Ganymede, Jupiter's largest moon orbiting right beside Europa, is heavily scarred from billions of years of bombardment. Jupiter is a gravitational vacuum cleaner that draws impacts in from all directions. The moons in its neighbourhood should be among the most cratered objects we have ever seen. Europa has almost no craters. Scientists have catalogued fewer than 24 confirmed impact structures on its entire surface. Based on how often objects strike in that part of the solar system, researchers have calculated that the visible surface of Europa is only somewhere between 40 and 90 million years old. In planetary terms, that is not just young, it is newborn. The dinosaurs went extinct 66 million years ago. The surface of Europa is potentially younger than that. Something is erasing Europa's craters almost as fast as they form, constantly recycling and refreshing the outer shell, pushing old ice downward and pulling fresh material upward in a slow, grinding planetary churn that never stops. That is where the creepiness begins. Because a surface that erases itself is not a passive, frozen landscape. It is a system, a dynamic, active, self-regulating system. And the question that falls directly out of that realization is, what is powering it? The surface temperature of Europa sits somewhere between -160 and -170 degrees Celsius. Europa orbits Jupiter at a distance of roughly 670 million kilometers from the Sun. At that distance, solar energy is about 25 times weaker than it is at Earth. You would need an extraordinary heat source to maintain an ocean of liquid water underneath a surface that cold, and the Sun is simply not that source. The answer comes not from above, but from the gravitational machinery that surrounds Europa on all sides. And once you understand how that machinery works, the existence of the ocean starts to feel less like a lucky accident and more like a calculated inevitability. Europa shares its orbit with 2 other large Jovian moons, Io and Ganymede. These 3 worlds are locked into a precise gravitational rhythm called the Laplace resonance. The pattern works like clockwork. For every single orbit that Ganymede completes around Jupiter, Europa finishes exactly 2, and Io finishes exactly 4. Every time Europa reaches a certain point in its orbit, Io and Ganymede are always in specific positions relative to it, and their gravity gives Europa a tug. This repeats indefinitely, hundreds of millions of times over geological ages, and those periodic tugs prevent Europa's orbit from ever becoming a perfect circle. This matters enormously. If Europa orbited Jupiter in a perfect circle, the gravitational pull on every part of the moon would stay constant, but because the orbit is elliptical, an oval, Europa's distance from Jupiter changes continuously. Sometimes it is closer, sometimes farther, and Jupiter's gravity, which is more than 300 times stronger than Earth's, is extremely sensitive to small changes in distance. When Europa swings closer to Jupiter, the gravitational pull increases sharply, and the near side of the Moon is squeezed. When Europa moves farther away, that grip loosens. This happens in a cycle repeated endlessly, and the result is that Europa is physically kneaded from the outside like a ball of dough, flexing and stretching by as much as 30 meters on every orbital pass, which takes just 3.5 Earth days. The friction generated by all that flexing creates heat. Not a tiny amount of heat, a planetary scale amount of heat, relentlessly generated year after year for billions of years without stopping. You can see the most dramatic example of this process on Io, Europa's nearest neighbour, which experiences even stronger tidal forces and has become the most volcanically active body in the solar system as a direct result. Europa is farther from Jupiter and less intensely heated than Io, but the tidal energy it receives is still enough to keep a global ocean liquid beneath miles of ice. Independent of sunlight entirely, no star required, just gravity, orbital mechanics, and friction. This concept, a world maintaining liquid water through tidal rather than solar energy, is one of the most important ideas in modern astrobiology, because it massively expands the zone in which life might exist. For decades, scientists defined the habitable zone as the narrow band around a star where temperatures allow liquid water to exist on a planetary surface. Europa blows that definition apart. The ocean beneath its ice is not in the habitable zone by traditional definition. It does not need to be. If life can exist anywhere there is liquid water, chemical energy, and a source of heat, then Europa is not an outlier in the solar system, it is a template. Now let us go deeper into that ice, because the ice itself tells a story that scientists have only recently been able to fully read. For years, there was a heated debate about how thick the shell actually was. Early estimates ranged wildly, from just a couple of kilometers to more than 30. A thin shell would mean easier communication between the surface and the ocean, faster material exchange, more dynamic geology visible from above. A thick shell would mean the ocean is more isolated, more protected, harder to probe. The argument mattered enormously for both geology and astrobiology. In September 2022, NASA's Juno spacecraft executed a close flyby of Europa, coming within 360 kilometers of the surface. Juno was not designed primarily as a Europa mission, but it carried a microwave radiometer that turned out to be exactly the tool needed to settle the debate. By measuring microwave emissions from multiple depths within the ice, the instrument essentially took an X-ray of the shell from the outside. The data, fully analysed and published in the months that followed, confirmed that Europa's ice shell averages approximately 29 kilometers in thickness. That is about 18 miles of solid ice between the outside universe and the ocean below. 29 kilometers is not a thin crust. It is a serious barrier, but it is also not a monolithic block of uniform frozen water sitting there doing nothing. The upper layers of the shell are extremely cold and rigid, functioning almost like a cap. The deeper ice, warming from the heat rising out of the ocean below, becomes more ductile, more plastic, and potentially circulates through slow convective movements, similar to the way Earth's mantle moves. The Juno data also detected tiny irregularities, small pores, cracks, and bubbles distributed hundreds of meters into the shell, though these are only a few inches wide and nowhere near large enough to form open channels from the surface to the ocean. Yet the ice is not static. Geologists describe a process called crustal delamination. Over time, the surface ice becomes enriched with salts and other chemicals deposited by radiation and other processes. This makes the surface ice denser than the cleaner ice beneath it. When it becomes heavy enough, slabs of that surface material can break away and slowly sink through the full 29-kilometer thickness of the shell like stones sinking through honey, eventually delivering chemical compounds from the irradiated surface down into the ocean. This slow conveyor belt of material is one of the primary ways the surface and the ocean might exchange chemistry without requiring open vents or channels. The Juno data also suggested something even more intriguing: the possibility of liquid water pockets trapped within the ice itself, sealed off from both the surface and the main ocean below. These are sometimes called perched lakes or brine pockets, bodies of saline liquid water sitting miles above the ocean floor, insulated from the worst of the surface radiation, but close enough to benefit from the slow, downward migration of nutrients from above. If life can exist in isolated subglacial lakes on Earth, like Lake Vostok in Antarctica, which has been sealed beneath 4 kilometers of ice for at least 15 million years, then these perched environments inside Europa's shell become deeply compelling in their own right before you have even touched the main ocean. That ocean, once you finally reach it in your imagination, is staggering. The ice shell ends around 29 kilometers down, and then you are in open water. Pure, dark, cold, pressurized water that descends approximately another 100 kilometers before reaching the rocky seafloor. The volume of liquid water in that ocean is estimated at between 2 and 3 times the total volume of all the oceans on Earth combined. It is a global ocean, wrapping completely around the rocky core of the Moon in an unbroken shell of liquid, sealed above by ice and below by stone. For a long time, scientists thought the ocean was primarily composed of magnesium sulfate, essentially Epsom salt water, based on infrared readings of the surface. More recent and refined spectroscopic analysis flipped that picture significantly. The yellowish stains and patches visible on Europa's surface appear to be sodium chloride, ordinary table salt. This suggests the ocean chemistry is not some exotic alien brine, but something much more familiar and much more Earth-like than expected. The water is estimated to be slightly alkaline, with natural minerals leaching from the rocky core constantly working to neutralize acidic compounds sinking from the surface, creating a chemical equilibrium that keeps the water in a moderate, life-compatible range. The ocean is not a still frozen lake sitting in darkness. Computer simulations have shown it contains powerful global circulation patterns. Because tidal heating is more intense at Europa's poles than at the equator, warmer water rises in polar regions and flows horizontally toward the equatorial zones, creating a planet-wide circulatory system. This circulation is critical for habitability. It means that heat, nutrients, and chemicals generated in one region of the ocean do not stay concentrated there. They are mixed and distributed throughout the entire global volume, potentially allowing life-sustaining chemistry to reach every corner of the abyss. The darkness inside that ocean is total. No photon of sunlight has ever reached it. Life on Earth almost everywhere depends on the sun, either directly through photosynthesis or indirectly through the food chains that photosynthesis supports. But we know from our own planet that this is not the only way. In the 1970s, scientists discovered hydrothermal vent communities thriving miles below the ocean surface in complete darkness, powered entirely by chemical reactions between superheated water and exposed rock. These ecosystems rely on a process called chemosynthesis, where bacteria convert chemical energy, particularly the hydrogen sulfide released by vents, into usable food. Tube worms, shrimp, crabs, and fish build entire communities around vents with no photosynthesis anywhere in the chain. If something like that exists in Europa's ocean, the ocean becomes an ecosystem waiting to be found, not just a body of water waiting to be explained. This is exactly why the question of what happens at Europa's seafloor became one of the most urgent debates in planetary science over the past few years. The assumption for decades was that something like Earth's mid-ocean ridges must exist there, where tectonic plates pull apart, exposing fresh rock to seawater, generating hydrothermal vents, and producing the chemical energy needed to fuel a biosphere. But a major study led by planetary scientist Paul Byrne, published in 2026, challenged that assumption in a way that forced the entire field to rethink its models. The study focused on the energy required to fracture rock at Europa's seafloor. For hydrothermal vents to exist in the classic black smoker sense, the seafloor has to crack open. Rock has to be exposed. Water has to penetrate into the crust. The stress generated by Europa's tidal forces on the mantle and seafloor rocks is approximately 150 kilopascals. That sounds substantial until you compare it to the pressure required to fracture the rock under 100 kilometers of water and 29 kilometers of ice, which comes out to more than 51 megapascals. The tidal forces are more than 300 times too weak to break open the seafloor under those conditions. Europa's rocky bottom is almost certainly geologically locked, quiet, and unable to generate the vigorous hydrothermal activity scientists had hoped for. This is a setback, not a catastrophe. Because life is remarkably creative when it comes to finding energy. Even without dramatic black smokers, other chemical processes can sustain a sparse, slow-moving microbial ecosystem. One of the most promising alternatives is serpentinization, which happens when seawater slowly seeps into the top few hundred meters of the rocky crust through tiny pores, reacting with silicate minerals and producing heat, along with hydrogen gas as a byproduct. Hydrogen is excellent metabolic fuel for certain microbes, and this reaction does not require fracturing or tectonic activity. It just requires time and the right rock composition, both of which Europa has in abundance. Another model, sometimes called the iron snow hypothesis, proposes that dissolved iron from the seafloor rocks could interact with radiation-derived oxidants gradually delivered from the surface through the slow crustal delamination process. The result is a low-level chemical reaction that produces a kind of respiratory substrate that anaerobic microorganisms could potentially use to sustain themselves. The ecosystem that could emerge from this chemistry would be nothing like a coral reef. It would be sparse, slow, cold, and microbial. But spare and microbial still means alive, and if life can maintain itself under those conditions, then the question of whether Europa is habitable gets answered with a quiet yes. Now here is one of the strangest and most counterintuitive things about Europa. The most dangerous feature of the Moon, the thing that would kill a human being on the surface in minutes, is also one of the most important reasons scientists believe life might exist there. Europa sits deep inside Jupiter's powerful magnetosphere. Jupiter generates a magnetic field roughly 20,000 times stronger than Earth's. The moons caught inside it are constantly pelted by high-energy particles, mostly electrons and protons moving at relativistic speeds. At Europa's equator, the radiation dose hitting the surface is approximately 5.4 sieverts per day. A dose of 5 sieverts over a few hours would be fatal to a human. The surface of Europa is one of the most radioactively hostile environments in the solar system. Those high-energy particles slam into the surface ice and trigger a process called radiolysis, literally the breaking apart of molecules by radiation. Water molecules, composed of 2 hydrogen atoms and 1 oxygen atom, get shattered. The lighter hydrogen, being so small, eventually escapes into space. The oxygen, heavier and more reactive, stays behind, building up within the ice. Over geological time, this process has loaded Europa's surface with remarkable quantities of oxygen and other oxidants, including hydrogen peroxide, sulfuric acid, and various chlorine compounds. The paradox is almost elegant. The radiation that makes the surface lethal is simultaneously manufacturing the oxygen that complex life would need to breathe and the chemical energy that metabolic processes could exploit. If those oxidants can somehow be transported from the radiation-loaded surface ice down through the 29-kilometer shell and into the ocean, they would represent a powerful fuel source for life in the abyss below, one that is being continuously replenished every single day by Jupiter's magnetic engine. The crustal delamination process described earlier, where dense, chemically enriched surface ice breaks off and slowly sinks through the shell, is the most likely delivery mechanism. But the debate about how efficiently this transport works is still active. Even a slow, inefficient delivery of oxidants to the ocean would accumulate to significant concentrations over millions of years. Some models suggest the amount of oxygen delivered to Europa's ocean could rival or even exceed the oxygen content of Earth's oceans. If that is accurate, the deep ocean is not just a place where microbial life could barely survive. It is potentially a place where complex aerobic life could thrive. The possibility of detecting signs of that ocean without landing or drilling comes from what some scientists believe may be happening at the surface even now: plumes. In 2012, the Hubble Space Telescope observed what appeared to be enormous geysers of water vapor erupting from Europa's south polar region and rising as high as 200 kilometers above the surface. That is nearly twice the altitude of the International Space Station. If those plumes are real and originate from the deep ocean, then a spacecraft flying through one could sample ocean chemistry without ever needing to touch the surface. In 2018, a team of researchers went back and reanalyzed data collected by the Galileo spacecraft during a 1997 flyby that brought it just 206 kilometers above Europa's surface. They found that Galileo had passed through a magnetic disturbance of over 200 nanoteslas and detected a sharp spike in plasma density over a 3-minute window, exactly the signature you would expect from flying through a water vapor plume. Galileo had likely sampled Europa's ocean chemistry directly without anyone realizing it at the time. Not everyone agrees the plumes originate from the deep ocean. Some researchers argue they come from pockets of liquid water trapped within the ice shell itself, pressurized by the freezing of surrounding material until they erupt through the surface. These crustal plumes would be chemically less interesting than deep ocean vents, because they would not carry the full signature of seafloor chemistry and hydrothermal interaction. But even crustal plumes would still provide a window into the chemistry of the ice and the brine pockets within it, which carry their own astrobiological significance. Europa also maintains a persistent thin haze of water vapour on its trailing hemisphere, generated by the slow sublimation of surface ice under constant radiation bombardment. This vapour continuously bleeds away into space, feeding a faint torus of gas that wraps around Jupiter in the same orbital band as the Moon. This is not dramatic or explosive, just a steady background leak of Europa's material into the Jovian system, one that instruments sensitive enough might be able to analyse without any plume event at all. All of these questions, the plume origins, the seafloor chemistry, the thickness and structure of the ice, the salinity and temperature of the ocean, the concentration of oxidants, the possibility of biosignatures, are exactly what NASA's Europa Clipper mission was built to answer. The spacecraft launched on October 14, 2024, aboard a SpaceX Falcon Heavy rocket from Kennedy Space Center. It carries a price tag of around $5 billion and represents decades of scientific advocacy, engineering development, and political will. Getting it off the ground was not a small thing. Europa Clipper will not orbit Europa directly. The radiation environment around the Moon is too intense for the spacecraft's electronics to survive long-term exposure. Instead, the mission design places the spacecraft in a large elongated orbit around Jupiter itself, swooping in close to Europa for targeted science passes, and then retreating back to safer radiation levels. Over the course of the mission, the spacecraft will execute 49 planned flybys of Europa, with some passes coming as close as 25 kilometers above the surface. The most sensitive electronics are housed in a thick-walled vault made of titanium and aluminum, using a radiation shielding approach proven by the Juno mission, which has been operating inside Jupiter's magnetosphere since 2016. The instrument payload Europa Clipper carries is extraordinary for what it has to accomplish. The REASON instrument, which stands for Radar for Europa Assessment and Sounding Ocean to Near Surface, is an ice-penetrating radar system that will beam radio waves into the ice shell, mapping its internal structure, looking for the perched brine lakes suggested by Juno data, and measuring the precise depth to the ocean below. MASPEX, the mass spectrometer for planetary exploration, will sample the trace gases and organic compounds drifting in Europa's tenuous atmosphere, and any plumes the spacecraft happens to fly through, building up a chemical inventory of the exosphere and potentially the ocean chemistry below. SUDA, the surface dust analyzer, will catch and analyze individual ice grains ejected from the surface and from plumes, measuring the composition of the material being thrown off the Moon. MIS, the mapping imaging spectrometer for Europa, will produce global maps of the surface composition, identifying where salts, organic compounds and thermal anomalies are concentrated and correlating those features with geological structures visible in high-resolution imaging. Together, these instruments will produce a picture of Europa with more detail and more chemical precision than anything achieved by Galileo or Hubble, and they will do it across dozens of flybys from multiple angles. By the time Europa Clipper completes its primary science mission, researchers will know the precise thickness and internal structure of the ice shell, the detailed chemistry of the ocean, whether plumes are real and where they come from, and whether the surface carries any organic compounds that survive the radiation long enough to be detected. At the same time, the European Space Agency's Jupiter Icy Moons Explorer, called JUICE, is also travelling to the Jovian system. Its primary target is Ganymede, the largest moon in the solar system, but the mission plan includes dedicated flybys of Europa. Combining gravity measurements from both JUICE and Europa Clipper will allow scientists to measure how Europa physically deforms under tidal stress, providing an independent way to calculate the stiffness and thickness of the ice shell from the outside in, cross-checking the radar data with purely gravitational measurements. Because Europa is considered one of the most promising places in the solar system to look for life, the mission operates under strict planetary protection rules. No terrestrial microorganism can be allowed to reach the European Ocean. To prevent any risk of contamination, the Europa Clipper spacecraft will be deliberately steered into Jupiter's atmosphere at the end of its mission and burned up completely. Removing the hardware from the European environment rather than allowing a dead spacecraft to drift and potentially impact the Moon over long timescales. What happens after Europa Clipper depends on what it finds. If MassSpex detects complex organic molecules in the Plumes, or if SUDA finds amino acids in ejected ice grains, or if Reason maps a vast network of liquid brine pockets just a few kilometers below the surface. The pressure to send a lander will become almost irresistible. A lander equipped with a drill, a mass spectrometer, and a set of biological detection instruments parked on Europa's surface would be one of the most consequential spacecraft ever built. Drilling even a few meters into the ice would get below the most heavily irradiated material and into a chemistry relatively undisturbed by charged particles, potentially preserving whatever signals life might have left behind. And this is where Europa becomes genuinely unsettling if you think about it long enough. Not frightening in the way darkness or monsters are frightening, but unsettling in the way that deep uncertainty is unsettling. There is an ocean down there. That is not speculation. That is settled science. The ocean is large, it is probably salty, it has been liquid for potentially billions of years, it receives a continuous input of both heat energy and chemical energy, and it is protected from the vacuum of space by a shell thick enough to maintain pressure and temperature stability almost indefinitely. Every ingredient scientists associate with the origin and maintenance of life is either present or potentially present in that ocean. The case for habitability is strong. What we do not know is whether habitability was ever taken advantage of, whether in all that dark, pressurized, ancient water, chemistry ever crossed the line and became biology. The answer is probably sitting somewhere below 29 kilometers of ice, waiting in complete silence for something capable of asking the question to finally arrive. Europa Clipper gets to Jupiter in April 2030. The flybys begin shortly after. And somewhere between the radar pings bouncing down through that ice shell and the mass spectrometer readings from plume material drifting through the exosphere, the first real data capable of answering that question will start coming back. Whatever is down there has been waiting for a very long time. Soon, we will start listening. If you found this as fascinating as I do, hit the like button and subscribe to join us every time we explore what the universe is hiding just beyond what we can currently see. There is always more out there. There is always more to find.